Thank you very much. So, yes, I'm going to give a slightly different talk to all the talks so far. I actually, the only connection to symmetric tensor categories I can think of is in my very first example, which is my favorite category, of course, is rep G for a reductive group G. So let me try to motivate my point of view, which is somehow this is the start of a new genre that hasn't been seen so far at the conference. My motivation is I'm interested in studying various abelian categories which appear in representation theory, like the symmetric tensor category rep G for a reductive group G, or maybe category of finite dimensional representations of all symmetric groups. This is at least an abelian category, and it's symmetric monoidal, but it's not rigid, so that's already not in the framework of the conference. But for me, it's a very important historical example where the techniques I'm talking about has been kind of developed and honed. Actually, another very classical example, that was not good, is just the classical BGG category O associated to a semi-simple Lie algebra. That's another of my favorite abelian categories. So I'm interested in the kind of combinatorial tools that representation theorists have to build to study these sorts of categories. So let me try and put it in a little bit of a general framework. I'm kind of interested in studying the strict monoidal category of what I call projective endofunctors of your favorite abelian category. My definition of a projective endofunctor is just a functor, everything's k-linear in the talk, just an endofunctor of the category which has both a left and a right adjoint, and those adjoints should be isomorphic. Often I'll be in a graded setting, so that isomorphism might incorporate some grading shift or something like that, so they might not exactly be equal. I think you all have seen this sort of techniques in representation theory. For example, if you're studying category O, classically the projective functors introduced by BGG are tensoring with finite dimensional rational representations of the corresponding group, so tensoring with V, and then the biadjoint would be tensoring with V star. Those are examples of projective functors in my sense. Or for me, if I'm studying representations of symmetric groups, induction and restriction from, for example, Sn to Sn plus 1. Any subgroup of a finite group, induction from that subgroup to the group and restriction back down again are an adjoint pair of projective functors in that setting. A little bit more generally, you could have any Frobenius extension of some algebras A and B, and then induction and restriction along that Frobenius extension give you an adjoint pair of projective functors in that sense going between these two different module categories. So these are the sort of functors that you have to understand to build the combinatorial tools to understand your original abelian category. If you actually want to get your hands dirty and really understand the examples of those categories, you have to deal with this issue. And I think a nice conceptual point of view is to actually focus on the strict monoidal category consisting of those projective endofunctors and natural transformations between them. There's been some really great success in the last 30 plus years in various wonderful examples of this philosophy where, in fact, we've managed to obtain presentations in terms of string diagrams for those strict monoidal categories, and it's really pushed kind of understanding the kind of general framework that's being used in all these different examples to work out combinatorics. So some of those wonderful examples are, for example, the category of Soergel bimodules. For me, I like as my kind of first baby example is Kovanov's Heisenberg category, which acts on representations of symmetric groups. The Kac-Moody 2 categories of Kovanov, Lauda, and Rouquier is another of my favorites. So I'm going to try and give you some sort of introduction to this, and I thought what I would do is I would actually just focus on SL2 for the entire talk. I'm just going to do SL2. It's already good enough to illustrate lots of important stuff. So I want to talk a little bit about Frobenius extensions. So this is going to be the source of these projective functors for us. It's going to be induction and restriction along Frobenius extensions. So there's a graphical calculus, there's a sort of string calculus for working with induction and restriction along a Frobenius extension. So I learned this from a cute little paper, but I think a very important one, by Elias, Snyder, and Williamson. The title is Cubes of Frobenius Extensions. So let's take a Frobenius extension of some commutative algebras. I'm assuming commutative because that's all I'll need in my examples, but that's just for simplicity. So Frobenius extension means that there's a trace map from the big algebra B to the small algebra A. My algebra, everything's commutative. So this should be an A-module homomorphism from B to A. If things weren't commutative, it would have to be an AA bimodule homomorphism. And then that needs to be non-degenerate in the sense that you need to be able to find a pair of dual bases, B and B check, for B as a free A module, and the dual bases with respect to the bilinear form induced by this trace map. So the trace of BC check has to be the Kronecker delta BC. So the point of that is that it makes induction from A to B isomorphic to co-induction from A to B. So the left adjoint of restriction becomes isomorphic to the right adjoint of restriction. So we're in this setting that these functors are some Frobenius, are some projective functors in my general sense. Okay, so I'm going to draw string diagrams to think about this. So I guess I'm drawing string diagrams in the two category of bimodules. So my objects are algebras. One morphisms are bimodules over a pair of those algebras, and two morphisms are bimodule homomorphisms. I'm going to really pretend everything's strict. So I'm really working with the strictification of that. Honestly, in my brain, I'm actually thinking in terms, instead of thinking about an algebra A, I'm thinking about the category of left A modules. And that bimodule, instead of thinking of it as a bimodule, I'm thinking about the functor given by tensoring on the left with that bimodule. And then a bimodule homomorphism I'm thinking about as a natural transformation of that functor. So that is how I think about the strictification of this two category of bimodules. If for my Frobenius extension, I'm going to formulate it in terms of the functors. So I've got induction from A to B. So that's just taking B viewed as a BA bimodule. That's the bimodule, and induction is just tensoring on the left with that bimodule. So in string diagrams, I'm going to draw the identity two-morphism, the identity endomorphism of that bimodule, if you like, as an up arrow. And the two cell on the right is going to be labeled A, and the two cell on the left is going to be labeled B. So I'm just using this usual string calculus. I guess I'm really drawing it in the strict two category of categories. Everything's k-linear, so the strict two category of k-linear categories. So that's very natural. That picture that represents induction from A to B, this bimodule. And then its adjoint restriction. So I guess that's tensoring with B viewed as an AB bimodule, but that's just, of course, restriction, as we all know. And there's the diagram for restriction, just a down arrow. And then induction is left adjoint to restriction, just in the usual adjointness of tensor and hom. So there's a unit and co-unit of that usual adjunction between induction and restriction. And so the string diagram for the unit of adjunction, so that's this bimodule homomorphism in string calculus. So that's going from A viewed as an AA bimodule to what am I doing here? I'm doing induction. So it's B viewed as a. I'm doing it badly. Yeah, so this is just the inclusion of A into B. That's all that is. Right? It's very easy, and the co-units just there. There's the string diagram. That rightward cap is my picture in string calculus for the co-unit of the usual adjunction, and it's just the natural multiplication map. These are totally canonical nice adjunctions. But because we've got a Frobenius extension, there's a second adjunction. There's an adjunction the other way around, making restriction left adjoint to induction. So this second adjunction comes from the Frobenius structure, and in string diagrams, I draw this as the leftward cup and the leftward cap. So these are non-trivial maps which depend on knowing that Frobenius structure. The co-unit of adjunction, so that's this AA bimodule homomorphism from B to A, that's given by the trace map in this Frobenius structure. And the unit of adjunction, that's given there. So it's a map from the bottom to the top. That's the way I draw my string diagrams. It's just the B bimodule homomorphism, just mapping one to that tensor product of your dual bases. So that's everything hopefully is really familiar there, but that gives us these rightward and leftward cups and caps. The example I'm going to be using this for, actually, my algebras are going to be graded algebras. They're going to be commutative graded algebras. And I don't want to really dwell on the grading, but I've added the word graded there. A graded Frobenius extension of degree D. That means that the trace map should be a homogeneous graded bimodule homomorphism of degree minus 2D. That's my convention. And actually, in the graded setting, what the convention from this Elias Snyder-Williamson paper is that you put a degree shift in the bimodule that you use for restriction. So there's the bimodule B for restriction. You shift that down in degree by D. I use Q for the downward degree shift function in this world. So the reason you do that, you put that degree shift in, is then it makes the degrees of these adjunctions, makes everything nice and symmetric. So with that degree shift, the unit of the usual adjunction, so that counterclockwise cup, and that counterclockwise cap, that's the co-unit of the Frobenius adjunction, both become degree minus D, and the clockwise adjunction maps become of degree D, and it's kind of nice to have that symmetry around. So that's kind of the standard convention. So I'm building this string diagram calculus for working with these Frobenius extensions for you. I think it's everyone's familiar with it, but somehow there haven't been any string diagrams before. So that's the only other obvious thing that you have in this generality is that any element of your commutative algebra A, multiplication by it gives you a bimodule homomorphism. So so if you have an element little a in your algebra, I will just put a little bubble labeled by A inside the 2-cell labeled by A to represent that bimodule homomorphism, the natural transformation of that identity function, if you're thinking in those terms. So where are our Frobenius extensions going to come from? Our Frobenius extensions are going to come from Coxeter groups. So I'm now going to quickly introduce the two category of singular Soergel bimodules. So this is going to have to go quite fast because it's a long story and I just want a little piece of it. But in general, I want to fix a Coxeter group W. I just write S sub I. I runs over the set N of nodes of the Coxeter diagram for the simple reflections in that Coxeter group. And I want to pick a suitable realization for that Coxeter group. I'm not going to write down what suitable means, but I want lots of conditions so that this is totally manageable for the cubes of Frobenius extensions that I want to be using to work. For example, to do this in positive characteristic, you really need some hypotheses.
So for these diagrams, you have the usual sync relations, but you don't have any relation on the somehow loops.
So far, I mean, these are adjunctions, so you have zigzag relations. That's all you've got in that framework so far. I haven't, but now we're coming to a concrete example where there will be lots more structure going on, coming from this nice realization of this Coxeter group. So my realization, I mean, you might think it's just the reflection representation of a Weyl group, for example, and I'm going to use R for the coordinate algebra of that reflection representation. So that's symmetric algebra of H star in this setup. And H is, of course, in degree 2 in this game. The Weyl group, the Coxeter group W acts on R by algebra automorphisms, and then R upper W is the ring of invariance there. And then we're going to be looking at parabolic subgroups of R indexed by subsets of the nodes of the Coxeter diagram. So imagine you've got subsets J sitting inside I. I always want these to be what are called finitary, which means that the parabolic subgroup Wi generated by those simple reflections is a finite Coxeter group. W itself can be infinite, it's totally fine. But this singular Soergel category really only makes sense if you restrict to these finitary parabolics inside here. And of course, little w sub I, that's the longest element of that finite Coxeter group. So that makes sense because of my finitary assumption. And I think I just write Ri as short for invariance for that parabolic subgroup Wi. And then the classical theorem of de Mazur here is that in this setup, the invariant ring Ri, which is a subalgebra of the invariant ring Rj, because you're taking more invariants, that's a graded Frobenius extension. The degree is just the difference of lengths. And the trace map, it's the product of de Maizière operators coming just from a longest one of these minimal coset representatives. So that's de Maizier's classical theorem, and providing you've got a suitable realization, it's true in this great generality. So what's nice in this situation, actually, instead of inducing from Ri to Rj for any finite tree parabolics, you can just go one simple route at a time. So we're going to just see these sort of induction and restriction operators when you're inducing from invariance of did I get that right? Did I get my I on the wrong side? Ri, yeah, that looks right. It's always I'm still getting familiar with this diagrammatics for this singular calculus. It takes some. So I'm only going to be going between kind of neighboring parabolics where I'm just adding a single simple root or removing a simple single root. And then, of course, transitivity of induction. So look at this diagram here. This is an upward crossing. So this is inducing from Ri to when I've added this extra ith simple root and then the extra jth simple root. So this is a composition of two induction functors. Or you could induce first to invariance for ij and then to I. And those two composites there's a canonical isomorphism between them that is what's depicted by this crossing here. So in these diagrams now I start coloring the strings by the simple reflections that I'm using. So this is like a blue string and a pink string, and you sort of, the strings are colored by the simple reflections that you're inducing. And this similarly, this downward crossing, this is restriction done either way. These two functors are isomorphic. And this crossing is the canonical isomorphism between those composites. Does that make sense to people? Once you have upward crossings and downward crossings, and we have all these clockwise and counterclockwise cups and caps, you can kind of rotate those crossings. So this is the upward crossing rotated using the adjunction through 90 degrees one way, and this is the downward crossing rotated 90 degrees the other way. In this setting, these turn out to be exactly equal, so you have this very nice kind of cyclic, these adjunctions are cyclic, and you get this very nice kind of strictly pivotal picture. The net effect is that in these diagrams, you can use isotropy as you would do in knot theory, for example. So this either way you prefer to define it, this is the rightward crossing, and similarly there's a leftward crossing in here. And then this is the full diagrammatic calculus for working with these sorts of bimodules and induction and restriction. So I'm going to write singular Soergel bimodules W. W is the fixed Coxeter group. This is the two category that I'm interested in to start with. So it's strict graded Cherubian two category. It's got this grading shift functor little q, so it's q complete. But it's just sitting inside the two category of graded bimodules, graded functors and graded natural transformations in there. And its objects are exactly these rings of invariance for all finitary subsets I of nodes of our Coxeter diagram. And then the one morphisms are what you get by, the one morphisms are generated as a two category, so you're allowed to compose horizontally by these inductions and restrictions between neighboring finitary parabolics. And by that gives you, by composing them, you get all of these induction and restrictions that fit into de Maizier's theorem earlier. So this is a very beautiful but difficult category in many ways, but it's very explicit. And Geordie Williamson's PhD thesis actually investigated this category. Those were before he was doing anything diagrammatic, but he studied this from an algebraic perspective, and he computed the Grothendieck category of this two category. So that's what I'm just going to write K0 of singular Soergel bimodules. For me, K0, I'm just passing to the graded Cherubi envelope. So I'm closing up with under this. Well, it's already actually here for singular Soergel bimodules. That's already built in. So, but I mean, take these bimodules and then I'm closing up so that it's Q-complete, graded, and Cherubian. So I'm taking direct sums and direct summands, and I'm taking grading shifts. That's all built into what I mean when I write SSBIM. And then this is just the split Grothendieck group of all the morphism categories. This collapses this 2 category down into an ordinary category. This is K0. And Williamson's theorem identifies this K0 in a very precise way, not with the Weil group, because we're doing singular Soergel bimodules, but with what's called the Hecke algebroid of the Weil group. So all its natural bases are labeled by pairs of, by minimal length double coset representatives for these finite tree parabolics. So it's quite a complicated setup, but it's a very beautiful theorem. In particular, that means he's classifying all the indecomposable singular Soergel bimodules. They end up being labeled by these minimal length double coset representatives. There's a homomorphism formula letting you calculate graded dimensions of 2 morphism spaces in this category. And so it's incredibly rich, rather wonderful combinatorial structure. So it's very rich combinatorially. And I've explained this graphical calculus so that you can kind of draw things fairly easily. And I feel like the graphical calculus is somehow necessary to make calculations in this general setting. Just very brief, but the diagrammatic calculus, this category is defined in an intrinsic way. This diagrammatic calculus is just a tool to visualize it. There isn't actually a full set of relations for this diagrammatics that I've described, but it's just there as a tool to work with the naturally defined singular Soergel bimodule category. So in general, it's extremely difficult, and sitting inside it is the category of regular Soergel bimodules, and that's already rich and wonderful in its own right. And but the things I want to show you today are some places where going to the singular setting is maybe reveals some extra interesting structure. So the rest of the talk is just going to give you a couple of examples which are related to SL2. Going back 25 plus years, I guess I first learned this example from this very important paper of Chuang and Rouquier, where they introduced the idea of SL2 categorification. So at the heart of that, I'm looking at special cases of singular Soergel bimodules from now on. And the first special case I want to tell you about, I call just Grassmannian bimodules. And so I call it GBIM sub n. So for this, I'm going to take the Weil group just to be the symmetric group Sn. And my realization that the ring R is just going to be polynomials in n variables. So we're just totally in a totally classical, wonderful setting. And I'm not going to take all parabolics. I'm basically going to take maximal parabolics. So I'm only taking the objects Ri there. I'm only taking objects, I'm going to use that notation, R superscript m, comma n minus m, associated to that parabolic Sm cross Sn minus m inside the symmetric group Sn. So I think the notation is totally, everyone's on board with it. So m is between 0 and n here. So I'm only taking these objects. So this is going to be a sub-2 category of the full singular Soergel bimodules for this Coxeter group. And so those are the objects I'm taking. I'm also not taking all one morphisms. I'm only taking some special one morphisms, and I'm going to write down the particular inductions and restrictions that you need to get this Grassmannian bimodule category. So are you ready for it? Here it comes. So here we go. So I'm going to, the bimodules that I'm going to be looking at, so there's the parabolic m n minus m. And this is a neighboring parabolic, m minus 1, n minus m plus 1. Can you see this? It's quite hard to write it down, but this is the best I can come up with. And the bimodule that I'm taking is actually not just an induction. I'm going to induce to this kind of 3-step with a 1 in the middle, m minus 1, 1, n minus m. So that 1 in the middle, that corresponds to, I guess, is the variable xm, if you're thinking about how these the symmetric groups just permuting our variables. So I'm inducing up to there, and then I'm restricting down to the kind of neighboring parabolic. Does that make sense? So I think the picture is very good. It's the best way I know visualizing what's going on. So I'm inducing and restricting to get from one of these maximal parabolics to the neighboring one. And you can also, so I call those ones E, just in general terms. Like going that way is E. And you can also induce and restrict. It's almost the same, except instead of going to the kind of the next parabolic up, I'm going to the next parabolic down. But again, it's an induction and restriction composition. So those are the bimodules that I'm using to generate this sub-2 category. It's too full, so I don't need to tell you about two morphisms here. And here I put a little picture which maybe helps you visualize what's going on. So these are all the parabolics that we're considering. E is a functor which kind of pushing you up that string, and F is a functor pushing you down that string. And you're meant to immediately think SL2, because that looks awfully like this SL2 string for this irreducible SL2 module. Okay, so that's just a little tiny, it's almost the easiest possible example. It's sitting inside this general singular Soergel bimodule framework, and it's totally classical. And as I say, I first learned about it from this Weiqiang paper. That was a first cite, a paper about representations of symmetric groups. That was the paper in which they proved Brouwer's conjecture for blocks of symmetric groups in characteristic P. And at that time, it was a total revelation. Inside representations of symmetric groups and induction and restriction from Sn to Sn plus 1, there was this structure of cohomology of Grassmannians was lurking inside there, and it was really a very striking moment when that connection was made. Okay, so so we've got Grassmannian bimodules now. So now I'm going to jump from Grassmannian bimodules to the 2 category associated to SL2. So this is meant to be this font that I can't actually draw. That's a sort of fractal font because it's a 2 category. It's the 2 category associated to SL2, which really evolved out of that Weiqiang work, but it took a little while to kind of get it into this for me natural framework. And so I've written Lauda and Rouquier down there. So Aaron Lauda came at this really from exactly the perspective that is relevant for this talk, and Raphael independently reached this definition of this 2 category. So this is a strict graded 2 category. Let me just really quickly write down the definition, because for many of you will have seen it already, but in my normal conferences, everybody knows what this is. So I've got a slide explaining. So it's a strict graded 2 category. The objects are just integers. They're just SL2 weights. And then 1 morphisms are generated by 1 morphisms called E and F. Actually, E is a 1 morphism going from object lambda to object lambda plus 2. So that's how I kind of write that down and F is a 1 morphism that goes from object lambda to object lambda minus 2. I think my notation is kind of natural, but maybe weird. And I draw the identity 2 endomorphisms of those 1 morphisms just by an upward string where the 2 cell on the right is labeled lambda. The 2 cell on the left for E would be labeled lambda plus 2, but I usually just write 1 2 cells label, then all the others follow. And F I draw as a downstring. So those are the 1 morphisms. You have to take horizontal compositions of those to get a general 1 morphism in this 2 category. And then the 2 morphisms are generated by these they're drawn diagrammatically. There's this upward dot, so that's an endomorphism of E, 1 lambda. There's the upward crossing, that's an endomorphism of E squared, 1 lambda. And then there's this rightward cap and this rightward cup. And I've written down the degrees there. The dot's degree 2, the crossing is degree minus 2. And then this is a presentation, so I'm now going to write down relations, and we're going to be very quick. So this is Raphael's a very optimal and lovely way of writing down all the relations as quickly as possible. It's very efficient. So to start with, there are relations on the upward dot and the upward crossing. And these relations are meant to remind everybody of something you're meant to know very, very well, which is the nil-Hecke algebra. And then, so the nil-Hecke algebra is underlying Schubert calculus in type A in every way. So you can see why I'm an imposter at the conference from this first relation. The crossing squares to 0, because this is coming from some de Maizière operator. De Maizière squares to 0. So, Braid relation as usual, and then there's this relation of how to slide a dot past a crossing. As I say, these are basically the diagrammatic way of writing down relations of the nil-Hecke algebra. Of course, the down arrow, the F is right adjoint to E, so these zigzag relations. And then in Raphael's approach, you can write down all other relations in one very simple way. You see, it's meant to remind you of SL2, right? So where I've just circled here, lambda is not negative. And in SL2, the commutator of E and F acting on weight lambda is meant to be acting as the scalar lambda. So really, I'm not working in SL2. I'm not really working with the enveloping algebra of SL2. I'm in this modified idempotent form for the enveloping algebra, where the commutator of EF 1 lambda is lambda times 1 lambda. And so this and this being isomorphic is somehow categorifying that basic Chevrolet relation in the enveloping algebra. And the way Raphael tells us to do it is he says, look at this matrix of two morphisms going from EF1 lambda to this direct sum on the other side. So it's a morphism to a direct sum, so it's written down by a matrix. And you can build this matrix using the generators that you have available. Sorry, there's a rightward crossing here, but you know how you get rightward crossings from upward crossings by using the adjunction to rotate. And the very slick way of writing down the relations is just to declare that this two morphism, or this matrix of two morphisms, has to have a two-sided inverse. I guess that's in the Karoubi envelope, in the additive envelope. That's if lambda's positive, and if lambda's negative, well, you can't, to get a positive formula that you can write down, you've instead got to pull the 1 lambda over to the left-hand side and have a direct sum with minus lambda times. So now you get a row vector of morphisms, which has to be invertible. And that's the complete presentation for this 2 category. So what I would like to say, it's a little bit tricky to say it precisely, but I think it's a good heuristic. This 2 category for SL2, it's Grassmannian bimodules, GBIM n, kind of in the limit as n goes to infinity. I think that's the right way to think about it. So it's kind of falling out of that little tiny, very special piece of Grassmannian, of singular Soergel bimodules in type A. So I guess a good theorem that convinces you that this is something to do with SL2, and maybe when you saw that Chevrolet relation, you thought it might have something to do with SL2, but here's an actual theorem that the split Grothendieck category of this 2 category, U of SL2, is isomorphic to this Lustig's integral form for this modified quantum group associated to SL2. So this is U dot SL2, and there's meant to be a ZQQ inverse to remind you that we're working with this Lustig form. These are isomorphic as, I mean, I guess technically they're categories, but I just like to think of them as being idempotented algebras. So they're isomorphic as idempotented algebras, with these idempotents being the lambdas, the integers that are the weights. So that makes it clear that indeed this 2 category is categorifying quantum SL2 in a very precise and natural way. These days I don't think that this is a difficult proof, but I wanted to write down just very quickly the steps in the proof. Basically, this is an argument following a paper of Kovanov and Lauda, where they wrote this down not just for SL2, and there's some issues, remain some issues. But very quickly, step 1 in the proof is that you work rationally instead of working over ZQQ inverse. So Q, remember, is going to come from the grading shift. You work instead rationally, and rationally, the homomorphism that you want is going to take the Chevrolet generator E for U dot to the isomorphism class of the 1 morphism, capital E, 1 lambda, and F is going to go to F 1 lambda. And it's almost immediate to just write that down rationally. Because of Raphael's inversion relation, it's just giving you that Chevrolet relation that the commutator of E and F is what you want. But then you've got to pass down to the integral version to ZQQ inverse, and this is much more work. So then the second step is, well, on this, you have a natural bilinear form coming just from taking graded dimensions of 2 morphism spaces in this 2 category. So this is this on the left-hand side, on this K0, there's a natural Hom form, and on U dot, there's Lustig's symmetric bilinear form on U dot, and you have to check that the Hom form matches Lustig's form here. So that's step 2. And then step 3, you have to then basically, you're trying to calculate this split Grothendieck category of this 2 category. You've basically got to identify the primitive homogeneous idempotence in your 2 endomorphism spaces here. So it's a naive theorem. You have to do the naive thing, and you have to construct all the primitive idempotents, or all the indecomposable projectives, if you want to think in those equivalent terms. But actually, in this case, it's rather easy to write down, because this is all driven by this nil-Hecke algebra that's lurking in the background. It's rather easy to write down candidates for primitive idempotents. So there's some natural idempotent endomorphisms of, for example, e to the power n. There's a natural idempotent. And so you write down these idempotents, and you check their idempotence, but how do you show they're primitive? Well, you show they're primitive by calculating the endomorphism algebra. Everything's graded, and you show the endomorphism algebra in degree 0 is just one-dimensional. And how do you calculate the graded dimensions of these endomorphism algebras? Well, the Hom form matches Lustig's form, so it turns out to just follow exactly from the almost orthogonality of the canonical basis for U dot. Once you show that the combinatorics of your homogeneous idempotence matches the combinatorics of the canonical basis. And that sounds scary and difficult, but this is SL2, and it's really easy and beautiful. So this is a quick guide to the argument. Honestly, step 2, even here, is a little bit of a challenge, because you can't get around it. You've got this 2 category defined by generators and relations, this U of SL2. You really can't avoid having to find a basis for 2 morphism spaces in this 2 category. And only then can you calculate this Hom form by taking graded dimension of your basis. And it's just, we're doing kind of stupid stuff with generators and relations. You have to get your hands dirty and prove a basis theorem. I've written at the bottom, the proof of 2 is the hardest here. You need a basis for the 2 morphism spaces. And honestly, for SL2, or indeed SLN, there's a nice argument by Kavanagh and Lauda. But for other other finite type is okay. I'm not totally happy with it in the literature, but I think it's there in the literature. For other Kac-Moody 2 categories, not SL2, maybe some affine Lie algebra or something like that, there's still actually no proof in the literature. But it has actually been solved by Ben Webster by what I call the new approach. He had a paper 8 or 9 years ago which doesn't solve it, but has the idea of the new approach. And I think it's finally reaching the point that the new approach has evolved enough that I believe it's correct. And I might, if I have time, say a little bit about it. Ben is still meant to be writing the new version of this paper with the new approach, with the correct proofs. But it's reached the point that actually I believe it. Even though there's still, the paper's not out there on the archive in a version that makes it. So anyway, so we're just doing SL2, and for SL2, everything's great. Actually, Aaron Lauda has a different approach for this SL2 case to proving this basis theorem for 2 morphism spaces. So somehow there's an obvious candidate for your basis for these 2 morphism spaces. There's kind of an obvious straightening rule, and you can see that the graded dimension matches Lustig's form. It's kind of simple combinatorics. But you have to prove the linear independence of the obvious basis. So you need your presented 2 category to act on something concrete where you can actually, it's stupid stuff, but it's the only way to do these things. Aaron's approach, and I think this was Aaron's entire motivation for his discovery of this 2 category U of SL2, was to relate it back to Grassmannian bimodules. So Aaron observed that there's a 2 functor from this presented 2 category to Grassmannian bimodules, G bim n for any n. There's a little 0 up here because you have to throw in some stupid extra object that's just a 0 algebra. So let me really quickly write this down because I want you to see that this U of SL2, it's related to these singular Soergel bimodules of this special type. So these are the generating 1 morphisms for the two category SL2, E and F. And here, in general, this was 1 lambda for any integer lambda. But if you can write your lambda as n minus 2m, n is fixed now, then it maps exactly to the induction restriction bimodule that I told you earlier that's inducing up to this neighboring parabolic. And F, it's induction restriction to the parabolic one before. All the other E and F 1 lambdas, they go to this extra object 0 that you just have to add in so that it really here you should put all BIM, all bimodules, and then there's no. And then, where do the two morphisms go? So here's the dot on the upstrand, the generating two morphisms. So the upstrand is this induction restriction, and the dot just goes to a bubble with that. Remember that xm variable corresponding to the 1 in the parabolic in the middle? You just need to put that x in the middle. Caps and cups, well, they go to caps and cups, but you can see it's sort of these, on the Cax-Moody side, I like to draw my strings thick. And then this functor is sort of splitting a thick string into a composite of an up and down, an induction and restriction of these thin colored strings so you have fun games with this. The crossing is actually very easy, but I just drew the picture just as a sort of pedagogical thing. So you see me using this string calculus for single Soergel bimodules to draw one of these maps. That's where the crossing goes. But actually the crossing in this setting is really very easy. It's just applying a single de Maizière operator corresponding to that variable xm, and then you can actually rather easily, you can do it with this diagrammatic calculus actually. You can check all the defining two relations for U of SL2. In this setup, it's actually an extremely quick calculation. I think originally it was rather difficult, but this diagrammatics makes it very convenient. So anyway, Aaron uses this to establish the linear independence of two morphisms, and I think that's a really rather nice and clean way. And philosophically, that's how I like to think of U of SL2 as this kind of limiting version of Grassmannian bimodules. Okay, so now I've got 5 minutes, apparently, to tell you about the subject of the talk, which is this nil-Brauer category. Unfortunately, I've set everything up so that I might have a chance of actually doing that. So I'm going to fix a parameter t, which is either 0 or 1, and I'm going to tell you about a new strict graded two category, nil-Brauer T. Think of this as the Brauer counterpart of U of SL2 from before. So it's got two generating objects, which I just call plus and minus. And then it's got generating morphism, which I just call B. There's a B that goes from plus to minus. There's its identity 2 endomorphism. And there's a B that goes from minus to plus. There's its identity 2. So there's just a single string, and two cells are colored plus or minus in this calculus. And then there's generating two morphisms, a dot, a crossing, a cap, and a cup. No orientation anymore on these things. I've written the ones where the rightmost region is labeled plus, but there's similar ones where the rightmost region is labeled minus. And the dot, like the polynomial generator in nil-Hecke algebra, is degree 2. The crossing is degree minus 2. And the relations very quickly. So this is like our de Maizière operator squares to 0. So so these are the relations for nil-Brauer. Braid relation as usual. The object B, its dual is the object B. Of course, it switches plus and minus when you go to that. But I think you see what's going on. This is some cyclic structure. So the dot kind of, you can pull the dot across a cap. You can pull the crossing past a cap. Curls are 0. The place the parameter t is 0, 1 comes in is the bubble. The bubble evaluates to the scalar t. You can only take t equal to 0 or 1. It's kind of forced by the other relations. So there really are only two versions of it. And then the most interesting relation is how a dot goes past a crossing, which looks a little bit like the nil-Hecke relation, but it's a little bit more complicated. Dot goes past a crossing, and you get two terms in there, cap or two lines. And I mean, it's quite natural in the space inside these two lines is actually labeled by minus, and that helps you remember that there's a minus coefficient. And so it's actually rather convenient working. You have to draw diagrams, which is never convenient. But once you face that fact to work with these presentations, it's not so bad. So that's the nil-Brauer category. And I've got to tell you really quickly what the nil-Brauer category categorifies. It categorifies the split I-quantum group of rank 1. So this is UQSL2 upper I. So so I-quantum groups, they used to be known as quantum symmetric pairs. It's Letzter's quantum symmetric pair associated to this it's rather a boring quantum symmetric pair, SO2 sitting in SL2. If you were to draw the Soergel diagram, it would be a single white node. Because SO2 is not a very interesting the algebra, and this split I-quantum group is not a very interesting algebra, but it's interesting as a co-ideal subalgebra of quantum SL2. So by definition, you take F plus Q K inverse E inside usual quantum SL2, and this I-quantum group is just a subalgebra generated by B. It's actually just a polynomial algebra in B.
What is K?
K, so this is quantum SL2, so my generators are EF and K. K and K inverse. So this is written in. So I use lowercase for those guys because I use uppercase for my functors. So Bao and Wang. So this name I-quantum group was introduced by Bao and Wang, and it's totally caught on. So I think that's now what they're called. They also introduced something called the I-canonical basis. So the generator for this I-quantum group is little b. There are these kind of divided powers, b to the n, which are a very special case of Bao and Wang's I-canonical basis. And in this case, this is such an easy case. It's nice when you get an easy case, right? Like for quantum SL2, you can compute the canonical basis. For this rank 1 split I-quantum group, you can compute the canonical basis explicitly. So here's a very quick definition of the divided powers as just this recurrence relation. So B0 is just the identity in this algebra, and then B applied to Bn, you either get quantum n plus 1, Bn plus 1, if n is congruent to the parameter t, or you get this lower term if n is not congruent. So this depends on the value of t, 0 or 1, the definition of these divided powers. So these span a rather remarkable integral form for this I-quantum group, and now you can guess the theorem that indeed the split Grothendieck category of nil-Brauer, K0nBt, is this I-quantum group. It's just a little bit awkward. I have to formulate it in a slightly complicated way because I've got this plus and this minus, these two objects. But morally, it's saying it's this I-quantum group. It's just some 2x2 matrices obtained very easily from that I-quantum group, and I don't want to say anything more about that. It's all perfect. The indecomposables in the 2 category, their isomorphism classes exactly match this I-canonical basis. The homoform on one side exactly matches a bilinear form on this I-quantum group, this Bao Wang Lustig form. And the strategy of the proof is very similar to Aaron's, and I'm not going to be able to say anything about it. I'd like to just get to the link back to singular Soergel bimodules in my last couple of minutes. But so those same 3 steps that I explained to prove the result for U of SL2, they work in this setting. It's just that they're all just so much harder, like barely possible by someone who's reasonably good at calculating. So it's kind of a miracle that this is in reach. The definition of the nil-Brauer category looks harmless, but it's extremely difficult actually to work with this. Somehow it looks awfully like the nil-Hecke algebra, but it's amazing how much harder the calculations are to get them to work. So I'm not going to say anything more about the proof. You have to first prove a basis theorem for the 2 morphism spaces, and we basically use this new approach. And I believe this new approach works uniformly for all of these Kac-Moody 2 categories, and we believe that there will be versions for all quasi-split I-quantum groups as well, and that when we finally have the courage, that this new approach will let you analyze those as well. And then, of course, at some point you have to construct the primitive idempotence in this 2 category, which match the same as the combinatorial recursion for this this I-canonical basis, and that's also a really hard calculation. But it's possible. It's always a miracle when you can write down the primitive idempotence exactly, and using this bilinear form is key to that. So just to very finally get back to singular Soergel bimodules. So there's also a counterpart of Lauda's theorem, this two-functor from U of SL2 to Grassmannian bimodules. For this nil-Brauer, what you need to look at these maximally isotropic Grassmannians in type D. So it's a bit of a mouthful. So I just called it something like IG BIM, isotropic Grassmannian bimodules. This is about the root system of type D. So there's my Dynkin diagram. I label the two n nodes plus and minus. So this has two different, this is Dn. It has two different an minus 1 subsystems, plus and minus. And then it has one an minus 2 subsystem, and I use I for those vertices. So we're looking at singular Soergel bimodules in type D, but I'm not going to take all of it. I'm just going to look at a little piece of it corresponding to these isotropic Grassmannians. So the only rings, the only algebras that I'm taking are these I plus and I minus invariants for these two an minus 1s. And the only bimodules that I'm taking, I'm doing induction and restriction from the plus an minus 1 induced to invariants for the an minus 2 and then restrict, or the other way around. Those are the two bimodules corresponding to B plus and B minus there. So a recent theorem which we proved now with Elijah Bodish and Ben Elias is the analog of Lauda's theorem from earlier, that there's a two-functor from this nil-Brauer 2 category to this bimodule category. I'm still not quite satisfied. There's some questions about describing the kernel of this functor, for example, by finding generators for the kernel, and we're still working a little bit. But I can just put my last slide up, which are just the pictures for this two-functor. So in nil-Brauer, the object plus, of course, that goes to the algebra of I plus invariants. Minus goes to I minus invariants. And then those are the generating one morphisms. They goes to these two special induction restriction composites in the singular Soergel calculus. The dot, so in type D, I'm just using the usual reflection realization in type D. So it's just polynomials in n variables. The simple root plus is x0 minus x1. And the simple root minus is x0 plus x1. You all know better than me how to construct the type D root system. So the dot corresponds to putting x0 inside there. That's an invariant for an minus 2 in there. The cups and caps, just as before, they go to nested cups and caps. And then the total miracle is this formula for the crossing. So this is drawn in this diagrammatical calculus. The orange string in the middle, that's a string of color 1, this exceptional node. And unlike the case of Grassmannians, where the crossing, I drew the diagram just for the heck of it, but it's extremely simple to calculate it. It's just a single de Maizière operator. This formula for the crossing, I know of no way to calculate it explicitly on the bimodules as a map. The only way I know how to work with this, verify my nil-Brauer relations, actually, the only way Ben Elias knows, because he's just a genius at calculating with this diagrammatics, it's fully within this diagrammatical calculus. The actual de Maizière operators that are involved are great big products of de Maizière operators, because actually this is kind of remarkable, this functor, but it's kind of beautiful. Okay, let me stop there.